Okay, we're going to talk about chapter 12.4. Chapter 12.4, which is curvilinear motion. Now, to begin talking about this section, we need to first recap what we did last time, which is the basic definition of acceleration, which is derivative of velocity, and velocity is the time derivative of position. So these two equations serve as the basis of all kinematics. In special cases, where we'll talk about the case when acceleration is constant. When acceleration is constant, what happens? What happens to this equation and that equation? And the result is you can find x, actually. S, which is the position, equals the initial position plus velocity times time plus 1/2 a t squared. Okay, so that's the first result when acceleration is constant. The second equation that we can come up with is velocity, which is equals to initial velocity, v naught, plus acceleration times time. And the third equation is velocity squared equals v naught squared plus 2 times acceleration times change in displacement. Okay, so with these three results, the first result relates displacement with time, okay, and the rest is constant. And by the way, this is initial velocity. And second equation relates velocity with time, okay, and the rest constant. The third equation relates velocity with displacement, and with the rest being constant as well. Okay, so we need these equations, okay, for curvilinear motion later. Okay, and before we discuss curvilinear motion, we also need to talk about special notation, where the symbol, okay, any symbol with a dot on top of it simply means the first derivative, okay, with respect to time. And anything with double dots on top of it means the second derivative. Okay? Okay, curvilinear motion can be analyzed using three coordinate systems. The first coordinate system is Cartesian, okay, which is I, J, K direction. Okay, these are the unit normals. The second coordinate system is called tangent normal. And with tangent, with the unit normal being ut, and normal direction with the unit vector being un. The third coordinate system you can use to analyze curvilinear motion is called radial and transverse coordinate system, with radial unit vector being ur, transverse being u theta. and we explore each one of these. Let's first talk about Cartesian coordinate system. So, using Cartesian coordinate system to analyze curvilinear motion, we can define x, y, and z, or I, j, and k coordinate system this way. Okay, and use right-hand rule to define the direction of I, j, and k. I, okay, sticks out your palm, your fingers, and wrap it around to the j direction, which is out this way, where your thumb is facing at the top of the k direction. Okay? So I, j, and k. Now we have a particle traveling along a curved path. Okay? And at any given instant in time, we can describe the position of the particle as x vector, as the position vector, equals the x coordinate, okay, I, plus the y coordinate, j, plus k coordinate, sorry, z coordinate, okay. When you take a derivative of position with respect to time, you get velocity. V equals simply x dot I plus y dot j plus z dot k. Okay, where x dot is exactly equal to the x component of velocity. Y dot is the y component of velocity, and z dot is the z component of velocity. And take the derivative further, and one more time, you can get the acceleration of this particle, which is x double dot I plus y double dot j plus z double dot k. And x double dot is exactly the x component of acceleration. Y double dot is y component of acceleration, and z component of acceleration. So, these are the Cartesian representation of position, velocity, and acceleration. Okay, for Cartesian coordinate system, it's most useful when you're trying to analyze the type of motion where it can be analyzed independently in each direction. Okay? When the motion in each direction can be analyzed independently. Okay? For example, the most common example of this type of motion is projectile motion. And let's look at what it looks like.